Hey everybody, Dr. A here, and in this video we're going to be exploring a virtual work example, but this time we're going to be analyzing a frame. So let's go ahead and get started. In the given information, we're being asked to compute the horizontal displacement of point C. And we see that point C is this roller over here. We're also being told that the flexural rigidity, that's the product of E and I, of member BC is equal to 2 times the flexural rigidity of member AB, okay? Now, the frame we have here is a 2-member frame. We have this vertical member AB, and we have it rigidly connected to this horizontal member BC. We see this kind of darkened triangle here symbolizes a rigid connection, or sometimes called a moment connection. So this is all considered one piece as it pertains to determinacy or stability. We have a pin connection at A and a roller at C. This vertical member AB is subject to this uniformly distributed load of 0.4 KLF, and it's 10 feet tall. And then the horizontal member BC is 8 feet long. So let's go ahead and dive into the solution. I'm going to start by saying solution. And the first thing I want to note is that we are going to, in order to calculate that horizontal displacement of point C, what we're going to do is place a horizontal virtual unit load at C. Remember, we place the virtual unit load at the point of interest in the direction of expected displacement. So we'll make a note of that. We're going to say place a horizontal unit load at point C, and we're going to point it to the right, okay? And obviously that makes sense, right? If you look at the real loading on this frame, this 0.4 KLF is pushing this frame, so we're going to get this kind of deflected shape that might look, you know, something like this, where this is going to be the delta C value that we're looking for, okay? So let's go ahead and do that. So here I'm going to say we're going to analyze the virtual frame, okay? The virtual frame. So I'm going to redraw this frame, except when I analyze the virtual frame, I'm not going to put any of the real loads on it. I'm only going to put the virtual load, okay? So this is going to be 1 kip. And what are these reactions going to look like? Well, we're going to have a C sub y, and of course there's going to be an A sub y and an A sub x as well. Now, I'll go ahead and put the dimension lines on here too, just kind of sneak them in there, 10 feet, 8 feet. Now, I need to establish my coordinate system, okay? Now, I could have done that at the very beginning. You know, sometimes in the given information, you're given these x values, maybe x1 and x2. Does it matter how we establish our coordinate system or our domains? Not really, as long as you capture everything that's happening on the frame. So here we're clearly going to have 2 domains. We're going to have the domain that defines AB, and then another domain that defines BC. And again, we have this kind of abrupt change defined by this corner B, because obviously you have this geometric change here. You round a corner. So you need 2 location variables. Now again, you can define them, you know, like as x1 and maybe x2 here. You can define it maybe x1 and x2 here. You could even do, you know, x1 and x2 like this. So you have some options. And again, when a problem does not define the location variables, then you can just do it yourself. So here's what I'm going to do. I'm going to define it myself, and I'm going to define this as x1, and then I'm going to find x2 pointing downwards. The reason I'm doing that is if I define my x1 and x2 like I just drew here on this virtual frame, then I don't need the reactions at A. I really only need CY. I can do method of sections, make a cut here, and look at a right free body diagram, which will include CY. And then later I can do another method of sections, make a cut here. Again, look at an upward free body diagram, also including CY. So you can avoid having to calculate these extra external reactions if you just define your X values strategically. And so that's what I'm going to do. Excuse me. So here I'm going to go ahead and calculate CY because if I do this strategically, I don't really need AX and AY. I could get them, but I don't really need them. So I'm going to say sum of the moments about point A equals 0. And we're going to say CY times 8 feet minus 1 kip times 10 feet equals 0. We'll do a little bit of rearranging, and we're going to get CY is 1.25 kips reacting upward. So that's just basic equilibrium to get CY. Now I can use method of sections to get my little m moment functions. That's what we're doing with the virtual frame. We're going to use method of sections to get our little m moment functions, okay? So first I'm going to say cut 1, all right? And I'm going to go ahead and draw my cut section right here. I've got 1 kip there. That's that virtual load. And then I have this 1.25 kips reacting here. That's the CY. And then what is this distance here? What is this distance to the cut? That's just going to be X1. And then, of course, I'm going to have my little m1, okay? Now, do I have a shear force and a normal force here? Absolutely, right? There's definitely going to be a shear force and a normal force here, little v1 and little n1. But am I interested in those for the purposes of virtual work? No, I'm really only interested in that internal little m1 virtual moment function, okay? And so here I'm going to say sum of the moments about the cut equals 0. And to establish this equilibrium equation, we're going to say negative little m1, and then we're going to say plus 1.25 kips times x1 equals 0. We can do some rearranging here, and we'll get little m1 is just 1.25 times x1. So that's my first virtual moment function. Now I need to make a second cut because I encounter that abrupt change, which is, that corner over here at B. So I'm going to go ahead and look at an upper free body diagram. So I've got this situation here. Here's this cut 2 here, okay, the second cut. Now, what applied loads are here? Well, I still have that virtual 1 kip here, and I still have that reaction at CY, 1.25 kips. And this entire horizontal length is showing up as 8 feet. And this little dimension here, this little nub of a dimension, what length is that? Well, that's x2, okay? Now, what's going to show up at this cut? Well, we're going to have an M2. That's what we're interested in. Is there a shear force and a normal force here? Yeah, absolutely, but I'm not interested in them. I'm really just interested in M2. So I'm going to go ahead and get that directly by saying sum of the moments about this cut equals 0. And I'm going to say that's going to be negative 1 kip times x2, and then plus 1.25 kips times 8 feet, and then minus little m2 equals 0. And then I can do some rearranging and get little m2. So 1.25 times 8 is just 10. So doing some rearranging, I get negative x2 plus 10, okay? And collectively, both of these moment functions carry units of kips times feet, okay? And so you can just, you can incorporate the units into the functions if you want, or just leave them out for clarity purposes. For now, I'm leaving them out for clarification purposes, just so my work doesn't look as cluttered, okay? Am I done? Nope, but I'm about halfway done. The next thing I need to analyze is the real frame, okay? So I'm going to say real frame. And I'm going to go ahead and just kind of redraw that quickly for us so, we know what we're looking at. Let me make it a little bit smaller for us just so I can kind of show it compact a little bit. And, of course, in the real frame, you have a CY and you have an AY and an AX as well. And the real frame is going to have the real loads on it, okay? So we'll go ahead and put these real loads, which was just this uniform load, right? And that's 0.4 KLF, 8-foot long horizontal member, 10-foot long vertical member. And again, I need to define the same coordinate system as I did in the virtual frame. So the same coordinate system will have that being x1, and, this is x2 right here. You've got to use the same coordinate system between your virtual frame and your real frame, okay? So here we're going to say sum of the moments about point A equals 0, and we're going to solve for CY in the real frame, okay? So we're going to say CY times 8 feet, and then I'm going to say minus 0.4 KLF times 10 feet times 5 feet, and of course that equals 0. So I'm going to get my calculator out, and I'm going to punch this through. So 0.4 times 10 times 5 divided by 8. So I get a CY of 2.5 kips, and that's going to be reacting upward because it popped out as a positive, okay? Now I'm going to need to go through a similar process I did before. I'm going to make a cut 1, just like I did before. So I'm going to draw that horizontal member. I've got this cut here. I'm going to have my capital M1 here. And, again, we've said this before. There's a V1 and there's an N1 there, but I'm really just interested in this M1, okay? And then my reaction was that CY of 2.5 kips, okay? And what is this distance here? This distance, is it 8 feet? Nope. Is it 4 feet? Nope. It is a distance x1, okay? And so here I'm going to go ahead and say some of the moments about that cut equals 0. So I'll have negative capital M1 plus 2.5 kips times x1 equals 0. So, of course, capital M1 is 2.5 times x1, okay? So that's my capital M moment function for that horizontal member. I need to do this one more time. Let's color code this. We're going to call this one cut 2, and we're going to make, draw a free body diagram here. Here's that M2 at this cut, M2. And, there's a normal and a shear force there that I'm not very interested in. And I do have a uniform load here now, right? Because I'm making a cut in that vertical member, which is supporting that 0.4 KLF. I've got this 1.2, I'm sorry, not 1.25, that was the last one. This is 2.5 kips reaction. This length is 8 feet. What is this length from the corner of the frame to the cut? Is it 10 feet? Is it 5 feet? No, no, no. It is x2, okay? And so now I'm going to use an equilibrium equation, say sum of the moments about the cut equals 0, counterclockwise positive. And so I can say negative m2, and then I can say minus 0.4 KLF times x2 times x2 divided by 2 is that moment arm, and then plus 2.5 kips times 8 feet, all that wrapped up equaling 0. So I can do some algebra and rearrange this. So I've got, I'll end up with negative 0.2 x2 squared, and then I will have plus 20, okay? And let's make sure the signs are okay here. Move this to the other side of the equation. So this stays negative, this stays positive. 2.5 times 8 is 20. Collectively, both of these functions have units of kip feet. So what do I do now? Well, now I apply my virtual work formula. What is the virtual work formula say? What does it tell us to do? It says we take 1 kip, which is that virtual load, and we say multiply by delta C horizontal. So that's delta CH for H is for horizontal, equals the summation as I goes from 1 to 2, because we have 2 domains, right? 2 domains of this frame, of the integral from 0 to L, little m, capital M, over EI dx sub I, okay? So we're going to add up 2 integral expressions, all right? So let's do that. Let's write this out one step at a time. 1 kip times delta CH equals, and I'm going to first express the integral of the, let's go ahead and do the horizontal member first. And the reason is because we called things associated with the horizontal member, the first cut, all right? So little m1 is 1.25 x1, and capital M1 is 2.5 x1, okay? So we're going to say integral from 0 to 8 feet, little m1, capital M1, over EI, and then we're going to say dx1. Now let's remember we wrote something special about this EI. Let's go back to the problem statement. We said that the flexural rigidity of BC is 2 times the flexural rigidity of AB. So watch what I can do here. I can say that this has flexural rigidity EI, okay? So remember, AB has flexural rigidity EI, and then BC is 2 times of that. So I'm going to say BC is 2 times EI. That's how we translate this statement right here. All right. So keeping that in mind, we put in the denominator here 2EI. And again, that comes from the problem statement. All right. Now that's member 1. Okay. So this is that horizontal member BC, all right, because we were calling that M1 and little m1 and capital M1. What about the next integral? We're going to say plus, we're going to take the integral from 0 to 10 feet of little m2, capital M2. That was just going to be divided by EI. There's no 2 times there. And then dx2. And then, of course, this is that segment, that domain AB, all right? So if I kind of expand this out, and I know I'm writing this one step at a time because I want to make sure we don't accidentally lose track of anything. 0 to 8 feet, little m1 was 1.25 x1, capital M1 was 2.5 x1, all divided by 2EI dx1, plus integral 0 to 10 feet. What was little m2 and capital M2? So little m2 negative x plus 10, and then capital M2 negative 0.2 x squared plus 20, okay? So let's see if I can remember that. Negative x2 plus 10 times negative 0.2 x2 squared plus 20, all divided by EI, and this will be a dx2 here, okay? So am I ready to evaluate these integrals? Sure. And these are pretty simple integrals. These are polynomials. So you could do them by hand if you wanted to, or you can go to a calculator. I'm going to use my TI-36X Pro, okay? So I'm going to perform those integrations there, 0 to 8 feet. I'm doing this first one here first. So you just want to punch this in carefully, 1.25x, and then times times, almost messed that up, times 2.5 times x again. We're going to evaluate that from 0 to 8. We also want to divide that by 2. So check me, but for this first term, I get 266.7 over EI. And of course, that numerator carries units of kip squared times feet cubed, okay? So, you know, each one of these moment functions has units of kip feet. You're multiplying them together, so you get kip squared, feet squared, and then you have this dx that goes from 0 to 8 feet. So that's how you get a kip squared feet cubed, okay? So that's what I got for the first integral. Let's see what we get for the second integral. I'm punching this in my calculator right here with you, so I encourage you to do it as well. So I get integral negative x plus 10. We're going to put a parentheses around that and multiply that by negative 0.2 times x squared plus 20. Wrap that up in a parentheses. And for this term, I get 833.3, also kip squared, feet cubed over EI. And so I add those two together, and, you know, I get 1100 basically. So if I were to write this out, I have 1 kip times delta CH equals 1100 kip squared feet cubed over EI. And finally, you know, if I cancel 1 kip with one of these kips here, I'll end up with a final value of delta CH is 1100 kip feet cubed, all divided by EI. It came out as positive, so this displacement is pointing to the right. It's pointing in the direction that we assumed, okay? So this is my final answer. It makes sense. If you did have values of E and I, you could substitute numerical values in for E and I. You got to convert units accordingly and be careful with that. But you could get a nice, solid, actual numerical answer if you knew what E and I were, okay? So that concludes this example problem. Hopefully you found this helpful. If you did, please hit like and subscribe and be on the lookout for other content like this. Thanks for watching.